Thank you, Mr. Chairman, for introducing me. Ladies and gentlemen, so this work, I'm just finishing to set myself. So this work has been carried out at Teyssier University in Limoges, and it's in continuity with the work we have carried out since decades in this laboratory regarding nonlinear devices, characterization, modeling, and instrumentation for nonlinear devices. So, how does it work? This way, I guess, yes. The outline of my talk, yes, obviously a quick introduction, and I will speak about an interesting multi-tone signal that will let us define a linearity factor that is pretty efficient. So, first, let's start with the introduction context of multi-tone measurements. So, we can approximate wireless signals with multitones for measurement purposes. That's done for a while. So we take an arbitrary wave generator, a given length of a given amount of time, and then we can repeat this measurement, and we can guess. We have a good statistics, and we can mimic a real signal. So we are it's very common to measure linearity of power amplifiers or maybe more things in the system with metrics like ACPR or NPR, adjacent channel power ratio or noise power ratio. And it turns out new modulations like OFDM regard more and more linearity. So it means the built-in peak amplitude power ratio is getting larger. So let's have a quick explanation, but that's very common for everybody. I think I will go very quickly. So if we apply a signal, so this is the one. If we apply a signal that has this bandwidth, so this is frequency, if we apply a signal that has this bandwidth into a nonlinear duty, and if we begin to saturate this nonlinear duty, the first thing we will notice is sideband. It's sideband adjacent channel, excuse me. So this is the first level of nonlinear effect, and then if you overdrive even more your amplifier, you will see more bounce around. So this is an IM3 effect. The first order is an IM3 effect, and possibly you can find some IM5, IM7 intermodulation products, more intermodulation products. And so the ACPR ratio can be derived from this, from real signal with band power measurement. If you just measure the power you've got here and the power you've got here and you make the ratio, you end up with this ACPR figure. That's pretty simple. So it's very easy to measure the real signals, and the spectrum analyzer, you need some integration time, but because you are playing with a real signal. So let's go to my measurement laboratory. And what's happening now? Now I will use an arbitrary wave generator, and I will define a given length sequence, and I will try to fit my nonlinear DUT with this, and let's try with a spectrum analyzer. So we attempt to build a wave with the arbitrary wave generator that has the same statistics as the real signal. Let's speak about a WCDMA, LTE, whatever you want. So same statistics, I mean the same peak to average, the same distribution over frequency, these kind of things. Obviously, doing this, we introduce arbitrary errors in our system, because we will decide the duration of the wave, the record size of the wave. We'll decide the tone spacing. That's more or less the same thing. The longer we'll have, the longer will be our sequence, the more tones we will have, and also the phase of the tones. So usually we make this kind of measurements. We repeat this measurement and we randomize phases, and we retry, and or we increase the number of tones to get accurate results. So let's look what's going on. Let's have a quick example with free frequency. So it's a very, very small multitone. Very, very small, but it's enough to understand what's going on. So in the beginning, I have these 3 tones, and let's suppose, because that's commonly used, they are equally spaced. So we end up with this frequency, F1 and F2. And if we go through a nonlinear DUT, and let's suppose we just deal with IM3 products. We forget about IM5, because we are trying to look at linearity. So we are not overdriving too much the device. So the first thing we see really popping up is IM3. So if we look at IM3, this is what we'll get at the output. We'll get some F0, F1, and F2, but also all the 2Fx minus Fy products, And also F0 plus F1 minus F2. And so we end up with 12 frequencies at the end. But these 12 frequencies, look, 2F0 minus F1 is equal to F2. And so on. So, in fact, here there's only one guy, but here there's two guys. Here there's the main guy plus another one. Here the same, the main guy plus another one. So you've got overlapping of tones. So that's very common. That's obvious if you have equally spaced tones. Can you measure this, the response, with spectrum analyzer? And can you end up with a figure of merit like ACPR with, okay, only 3 tones? Okay. But no, the response is no. No. Why? Because of phases. Because, in fact, if we are playing with spectrum analyzer, we are measuring powers. And so here, we are adding power, but in fact we are adding waves. So they are phases. And here I try to mimic this with this, but it's phasors we are adding. We are adding. So the power we get is not if we randomize the phases, if we change the phases of these 3 signals, we will end up with a different figure here, with different figures. So the only way is maybe to do a lot of measurements with random phases, and that's not very convenient. So in fact, it's very difficult. I cannot end up with just a spectrum analyzer, and with this setup, even if I play with more frequencies, 3 is not enough, I will not end up with a good ACPR figure. So let's try to design a multitone that will try to make things better. So we are very close to Christmas. So let's make a wish list for Santa. So all the things I'd like to do is first I'd like to have a multitone that let me control the peak to average, because that's one of the big things when we are dealing with nonlinear devices. We saturate when we go to peak. I want to have accurate measurements with various receivers, maybe including NVNAs. Why not? And you will see that it's a good idea. I want to have fast measurements of a multitone. And I want to end up with a figure of merit that can be measured in production environments. Because it's now more and more demand of industry. With power amplifiers, you have got everywhere with Internet of Things and whatever you want. You will end up, it will be a spec, EVM or something like that. Manufacturers will have to provide a spec for this. It will end up this way, I'm pretty sure, very soon. And last thing is, let's try to design a linearity metric, figure of merit that is more general, because most of this ACPR or EVM, or yes, EVM, but no, I don't want to speak about EVM. ACPR or NPR, because ACPR or NPR is more or less the same thing. You're just looking at different areas, but it's the same thing. It's spectral rigor. They depend on a given modulation, and that's not very agnostic. I have a duty. I want to have a figure of my duty. Obviously, for this given modulation, I want to know that it's nice. It would be nice to have a figure that is more general for my duty. So let's try to build this. And this is the 2 choices we have made, and I will go into details later. It's first, let's set all the frequencies on a Fourier transform grid. Okay, so it will help a lot for measurements. Say, we'll run instruments, we'll run receivers, Fourier-based receivers. That's very common now with new spectrum analyzers or some other instrument like LSNA or NVNA, some NVNAs. So we'll run, so having all the tones on the Fourier transform grid will be very convenient. And try to avoid any overlap of IM3 products, because if I can avoid this, I will be very happy. If I can measure independently, if I can measure independently all these 12 frequencies, I will be very happy. Because then it will end up with only power measurements. I will not need any more. Scalar measurements will be enough. I will not need any more vector measurements to understand what's going on. So this has some direct consequences, these 2 choices. All the IM3 and also higher IM products will be on the same grid, somewhere else, but on the same Fourier transform grid. And the relative phases of stimulus do not matter anymore, because I will avoid overlap. If I avoid any overlap of the signal, I will not have to take care of the phases. It has also some derived consequences. If I use a Fourier transform-based instrument, I will not need any more windowing. If I just set properly my receiver, if I set the good length of good acquisition length, I will not have to set anything. There's no need, obviously, to do a huge number of tones or phase randomization, so I can end up very quickly with a figure of merit, so that's compatible with industrial needs. And we will see even better news about peak power ratio. Peak power ratio. So let's build a multi-tone with this equation. Usually we have only this part, and we just add a small parameter. So usually, if equally spaced frequencies, it's like this. This F1 is the main RF frequency, and then we offset this, and delta F is the average offset frequency. So let's have this figure, a multiple of my Fourier transform grid. My Fourier transform grid can be 1 kilohertz, let's say, for example. So let's have this figure, multiple of my Fourier transform grid. And this small parameter is a small offset, but it's not unique. There's one for each K. It's a small offset applied to each stimulus frequency, but it's also, the absolute value we get is also a point in the Fourier transform grid. It's a value that is a multiple of a Fourier transform grid. Okay. And so this epsilon series is arbitrary under constraints. So we can find many different of these epsilon k series that will fit our requirements. And I will speak a little bit more at the end of the talk. Oh, the colors are not very good. So this is exactly the beginning of the table you've got in the paper. And this is a free-tone example. So I set free tones around 2 gigahertz something. So I can guess I have a perfect receiver. I don't have your trouble, John. I will guess I have a perfect receiver and perfect system, but okay. And so F1 and F1 here is F1, F2, F3, and when I compute all the frequencies of the 9 for free tones, we end up with 9 intermodulation products. We have run this up to 8 tones, and then you end up with 224 intermodulation products. But that's still very easy to have them all apart. You see, you never see twice the same figure, never. But if you look at the intervals between any of these frequencies, it will be a multiple of this figure of the Fourier transform grid. Okay? So, that's pretty easy. What's the consequence? Oh, let's speak about peak to average. What is the peak to average of this signal? Wow, there's a very good news here. As the tones are non-equally spaced, we end up with a signal trajectory in the complex plan that does not depend on the relative stimulus phases. So that's consistent. I was telling you before, if I just measure power, if I avoid any overlapping, only power measurements will let me end up with an ACPR-like ratio. And this is more or less another way to say the same thing. Obviously, this is a first-order affirmation. The higher the number of tones, the better it works. But let's look at a 4-tone signal built in the way I showed previously. This is the trajectory. So it looks like a circle, and you don't see any spikes around. And if you go to 8-tone signal, this is a simulation, and this is a measurement. If you go to 8-tone, you really see very clearly the circle of a trajectory. So you don't go out. So it looks, and you can play with the phases. You can randomize the phases. 10 minutes? 10 minutes left? No, oh, don't be sorry for Mr. Chairman. This figure is wrong. It's 25. I'm very sorry for stressing you. I have only 25 slides, but I made a wrong. I forget to make this automatic. Sorry for it. So the peak to average, and it turns out that the peak to average of this kind of signal is extremely simple. The math to demonstrate this are very complex. It has been demonstrated by one of the authors of the paper, Jacques Sombrin. It's a big, big demonstration. But you end up with an extremely simple formula. Extremely simple. The peak to average with this signal only depends on the number of tones. So with 8 tones, we end up with a peak to average, which is 9 dB. And with 16 tones, we get 12 dBs. That is more or less what is the peak to average required for OFDM. And 9 dB is very common is in the range of what you need for WCDMA or this kind of thing. So that's an extremely good news, and we get this also in measurement. That's a very, very good news. The peak to average of this signal is well known, and we can change it just by changing the number of tones with a very small number of tones. In fact, this formula gives the upper limit, this gives the circle that is around. And we are just inside, but very close. So let's measure this signal. So because in my lab we are very happy with LSNA and all these sampler-based receivers. So we did this with a receiver, with this kind of receiver. So we have an arbitrary wave generator. We measure DUT. We don't have played in this paper with tuner. The load was just 50 ohm, but obviously this is for future. We plan to go to that direction. And so we are playing with this VTD receiver that is exactly the son or the equivalent of the LSNA, but also modern spectrum analyzers are Fourier transform based, so you can make them to fit exactly the Fourier transform grid. So if you do this, you end up with no windowing and very, very fast and accurate measurements. So because it's a key advantage, we can check the multitone before and after the DUT, because we are in a network environment. Okay, we'll see what it will give us. So, yes, a quick slide to explain. That's a slide I love because I've spent so much time with sampler-based stuff. So to explain a little bit how sampler-based stuff works. But okay, I think I have not too much time. So let's go on. Let's go on and let's go to the same table as before. This table is in the paper. You can find in your handbook. And let's look at what we get, the power we get from this measurement system at minus 10 dBm if the arbitrary wave generator is set to minus 10, plus 6, plus 13, plus 16. And I will be back after to this column. And also I will be back after to the figure of merit. So I will be back to this slide after. But right now, let's have a look. So if I play with minus 10 dBm, my amplifier is very linear. Okay, so I end up with some figure 3 times more or less the same figure because I apply the same amplitude to each tone. I end up with the same amplitude for each tone, and all the other tones are in the noise. Okay, it's not a high dynamic range measurement, but the noise is in the range of minus 80. If I increase a little bit, still the same thing. If I go to plus 13, yes, now I'm running nonlinear because you can see now these guys are popping up, clearly popping up, and you find out that they are more or less all the same value, this one, and these 3 ones are a little bit different, but that's, if you go to the math, you will see that this one will end up with 6 more dB. So that's consistent. So if we drive even stronger, then we end up with figures that are still very consistent. Let's have a look at what we get out of a Fourier transform of the instrument. I'm running the swap in an uncalibrated mode. Just getting out at 2 gigs, I suppose the response is flat enough, so it's only relative measurements. Because at the end, if I want to derive something like ACPR, it's a ratio, so I don't need real absolute things. But here are my main 3 tones. Here are the 3 tones that are bigger because it's the 3 last tone of the table. Here are the 6 guys. You have seen the 2 fx minus fy. And then here below, you've got the 5th and 7th order product that are on the Fourier transform grid but that don't overlap. That's one of the nice properties. If you choose carefully the epsilon k factors, you don't overlap. But here they are pretty high because I'm overdriving a lot of the device. But if I don't want to go that far, just to measure linearity, I don't need to go that far. Then, okay, I want now to measure a big device. A big device means I need a big excitation. A big excitation means I need a big power amplifier before my device. And I don't want to measure the power amplifier of my measurement setup. I want to measure my DUT. So it means I will like to try to predistort things. Let's go back here, and imagine this is my power amplifier and this is my DUT. If I drive here very strong, what I will measure in my receiver, I will measure the IM3 products from this guy and from this guy, both of them. No way to really make a separation. Yes, now there's a way. There's a way because I can measure before and after the DUT. So I can just have a quick loop. Let's first overdrive this guy and have a look at what I get here. I will get the same kind of things. I will get IM3 products everywhere. But because I'm in a vector environment, I can get the amplitude and the phase of this guy. So I can just feed this back to arbitrary wave generator. So I've still my 3 main guys, but my 9 other guys, let them just with the same amplitude and opposite phase compensate a little bit. That's just a predistortion. And this is this column. This is this column, so you see that we make things going compare plus 16 without and plus 16 with the predistortion. We make all the IM3 products getting lower, and here it's not really optimized. We can have a loop on top of that will fine-tune everything to get a little bit better stuff. So, thanks to the vector measurements, yes, we can achieve very quickly some compensation factors to feed in the arbitrary generator. So we end up with a measurement setup that is much more linear, even if we are playing with high power. From the DUT point of view, we feed the DUT with only 3 tones, because we have tried to make down all the intermodulation products coming from the amplifier for my setup. Also, we can have some IM3 products that can come from my receiver, because also my receiver inside, my sampler can be is a nonlinear guy. So if I overdrive it, I can get some IM3 products coming from this. But okay, this is pretty easy to address. This is the usual technique people are using every day with spectrum analyzer. You just add an attenuator. That's easy. And so we can see, I don't want to spend too much time, but so we can see the benefits of predistortion in the last column of result. That's just what I commented. But, okay, so this setup, we can go fast. We can, because we are Fourier transform based, so only one measurement, very quickly. We don't have to randomize the phase. Okay, but I show something with a network analyzer. That's still pretty expensive, but let's imagine we have a poor guy. Oh, if I just have an arbitrary wave generator and spectrum analyzer, I can still do it. Because it's vector measurements. The only trick will be it will take me a little bit longer if I want to have a predistortion, because I will have to have a loop to optimize for the phase because I don't have this information. But do I have to do this all the time? No, because it's for a given, I just need to have a table for a given power level, because I can hope my measurement amplifier and all my arbitrary wave generator side is stable over time. So this measurement can still be done very quickly and very accurately with something pretty old-fashioned or whatever you want. Let's speak a little bit about the linearity factor. From the work I have done, we can define a linearity factor. So let's call it a multi-tone linearity factor, MTLF. And we can compute the sum of the wanted power we get, the amplitudes we get from F1, F2, F3, for example, if we have a 3-tone example, divided by the sum of the power we get from the 9 IM3 products. And we can normalize this in order to get a consistent figure if I go to 4 tones, 5 tones, 8 tones. So the second part is a normalization factor. And what we end up with these figures. This figure of merit of the amplifier measuring for a given power level. It turns out, we need to carry out some more work about that, but it turns out the behavior is extremely, and I hope we'll end up with saying it's exactly the same, but I cannot say today, the same as ACPR or NPR. So this factor is shown in the result type, yes, and it's extremely stable. And I can play a lot. I can try to randomize to make several measurements of the same setup, randomizing the phases. I get always the same value. And I've tried to have a look in the swap. It's possible to have a direct access to ADC record, ADC data, and I checked that the mean and max of ADC record I get in IF band are always the same. So it's, in other words, my peak to average does not change. Obviously, yes, just a small detail. Running this with NVNA, it runs well only if your modulation fits, all your frequencies fits in the IF bandwidth. Otherwise, it's getting tricky. So this is why, at the end, I think we should consider this MTLF as a new metric for linearity. Because it's more agnostic versus modulation, we don't need to play with so many tones. Only 8 tones can do a great job. Peak to average is monitored, so that's equivalent. That's more or less saying the same thing. Because I monitor peak to average, I don't need not that much tones. I know exactly what I'm doing. So it's phase invariant, and it's very fast and accurate. It can be done with many different receivers, and we can imagine to do this in production environment. Because it's, with a swap, it's a matter of, let's say, 1 or 2 milliseconds to get one measurement, because it's just one acquisition, compute the power, make the ratio, and we're done. That's it. Yeah. So conclusion and perspectives. So we have proposed a pretty simple multitone signal with a limited number of tones. It gives very quickly very similar results with NPR or ECPR measurements. There's something here in perspective we plan to work. We can shape this signal to ensure the best coverage of low-frequency memories. Oh, I told you there's this epsilon k theory. We have some degree of freedom on it. We need to choose it to ensure there's no overlap, but we can also choose it to optimize the coverage of a low-frequency memory, to have tone spaces that will coverage a given time domain or low-frequency memory effect domain. That's another way. So that's why I think we should consider this as a candidate, not the best, but not the worst, as a candidate for a linearity factor standard. Thank you for your attention.